Okay, so I think we can start. So it's my pleasure to open this very exquisite session on turbomachinery today in the workshop. And the first speaker is Gavin Tabor, and he's talking about coupled fluid structure modeling of a wind turbine blade.
Yes, coupled fluid structure interaction modelling of a wind turbine blade. I put myself as first author, but in reality all the work here has been done by my PhD student Rachel Smith, supported by Makis Trodakis, who is the guy who's sitting over there rather, and his supervisor Benjamin Yakiman. So I take credit for any mistakes I make in the presentation, but nothing else here. Right, so I'm pretty sure nobody in the audience seriously doubts that we need to diversify and decarbonize our sources of energy. And so this is the motivation for a lot of work on wind turbines and wind turbine energy. Particularly in the UK, we have a very significant wind resource in the UK and a very significant offshore wind resource, in common with other countries around the North Sea, but other areas as well. And the years from about 1985 onwards to 2020 has seen an inexorable increase in the size of wind turbines. Early wind turbines were on land, but for various reasons they've now moved offshore, and this is not merely because of NIMBYism. There are some excellent reasons for building offshore wind turbines, not least of which is the size and the available wind resource. So turbines get larger every year, and this is in order to intercept more wind, obviously, and to intercept a better wind resource as you move them higher and higher into the atmosphere. At the same time, we want to build them more efficiently, so the blades themselves, there's a constant drive to make them lighter, both in terms of manufacturability, but also in order to make them work more efficiently. And so you have to address the question of the aeroelastic deformation that you're going to get from a long, slender aerodynamic structure in a high crosswind. It's going to flap around. It's going to be like the tips of the Boeing 747 moving by a metre upwards when it takes off. And so there's a great interest in coupled simulation, fluid structure coupled simulation, in order to predict and hopefully help us design these turbine blades. So, area of fluid structure interaction here, we're solving coupled equations here, coupled systems of equations. The fluid flow, the airflow around the blade, coupled with stress and deformation in the blade itself. So we've got a two-way coupling. The flow produces forces on the solid, on the blade itself, and we could leave it at that. We could just predict those forces. We want to do the two-way coupling. We want to predict the displacement of the wind turbine blade, and that will lead to a change in the domain geometry for our CFD here. Now, a couple of weeks ago, I was hosting a hackathon on fluid structure interaction at Exeter, and various of us, including Makis, got involved in quite a long discussion about terminology, how we distinguish different approaches to doing this. And I'd like to distinguish monolithic and coupled approaches based on what we're doing with the codes. Basically, to me, monolithic means solving all of these physical equation sets using one common solver. So, example being solids for foam, very good example there, versus a coupled approach where you're taking hopefully best-in-class various solvers for the different physical problems and stitching them together using some sort of code during the communication between the different domains, basically. And that's what we've done here. We're coupling OpenFOAM to the open source FEA code Calculix using the Precise coupling library. And if you're not aware of Precise, I would encourage you all to go and have a look at it. It's a very interesting tool for doing this sort of thing. So I'm going to present two pieces of work here, which are along the lines of a proof of concept of doing this. And the first one is to do some level of validation. So Rachel found an interesting standard test case, which is a cantilever beam and cross flow. And there's a paper here which provides actually both experimental and computational data for this problem. I'm going to jump ahead, actually. This is the mesh used here, and I think it gives an illustration of the cantilever beam there. That's a pink item standing up there inside the domain as a whole. I'm guessing from the fact that it's limnological oceanographic that it was intended at, I don't know, kelp forest modelling or something like that, but it's a good example of a flexible cantilever beam in a cross flow. The experiment uses a rectangular silicon foam plate fixed at one end. It's fairly floppy, so you'll get a reasonable amount of displacement here, using incompressible laminar flow here, and a non-linear structural solver on the Calculix side, and coupling using nearest projection mapping and IQN-ILS coupling there. There's the geometry, and here are the results. I've reproduced Rachel's table here. The experiment represents the experimental information here, drag coefficient and displacement of the tip in the x direction, which is the direction of flow, and of course it doesn't lengthen, or I don't think it lengthens, so as it bends the tip moves down, so there's a z displacement which is negative. And the same paper gave calculations using code using buoyancy terms and no buoyancy terms, and we were using I think it's icofoam, so no buoyancy here. So there is a pleasing degree of agreement between all of the values, and in particular between our calculations and the equivalent zero buoyancy ones, so the two right-hand columns there. So this indicates a degree of certainty that we're at least doing the calculations correct. I hope so, anyway. So moving on to the actual work Rachel did here on the wind turbine blade, we're using the DTU, it's Danish Technical University, I think, 10 megawatt reference turbine blade, which is a very standard case in wind turbine research here. She used the same basic geometry, so blade length, width, and shape. The actual turbine blade itself has a somewhat complicated structure. So inside here there are webbing elements which give it a degree of rigidity. She started off trying to reproduce that exactly, but after a while decided to lose those and produce a simplified structural model, basically just the shell of the wind turbine blade. That, of course, has some consequences for the results here. The left-hand diagram here, by the way, indicates the nomenclature you were using. So flap-wise bending is doing that, whereas edge-wise bending is that direction. And because of the lack of the internal geometry, so the different vibrational modes are significantly different from what they would be for the actual wind turbine blade itself. But we're doing this as a numerical experiment, so it's not that significant. It also affects the stiffness along the blade, so these graphs here indicate what's going on, and the difference between the model blade and the DTU blade at any point along the blade there. Okay, so FSI set up simulation. For the simulation, this is the fluid domain set up using snappy hex mesh on a cylindrical mesh, and the blade is in the middle there, anchored at the bottom, and a certain degree of refinement around the blade. We've done, or Rachel has done some, the beginnings of a mesh refinement study, so at least a mesh sensitivity, 3 meshes going from 500,000 to 3.5 million cells here. Enough to demonstrate the technology, not, we admit, enough to get to any degree of, or to a pleasing degree of mesh independence. We would have to go a bit further, but we were interested in a short project to demonstrate the technology here. On the Calculix side, Calculix, in case you're not aware, is an open source FEM code, and it's, I may be wrong here, I think of it as a open source clone of Abacus. It seems to share some features, including the file formats, for example. Rachel built a structural mesh of the blade with 4,400 tetrahedral shell elements there. When the mesh gets read in at the beginning of the calculation, the initialization, those 2D elements get expanded into equivalent 3D elements. So this is a shell which is 1 element thick at all points. And that's the mesh there. At this stage, we were working on stationary blades. We want to move this to rotating blades. Haven't got that far yet. And we're looking at 2 wind speeds, 12 meters per second, which is a fairly reasonable day-to-day wind speed, and 50 meters per second, because one of the things we're interested in here is response in extreme wind conditions. Using incompressible RAN simulation, Spalart-Almaras turbulence model. Again, the mesh resolution here isn't quite good enough to get the correct Y+ values, but is going towards that. And again, geometrically nonlinear structural solver, and IQN, ILS acceleration, and radial basis functions for the mapping. And yes, it does work. Excellent. This demonstrates we're getting fluid structure interaction. We are getting the 2-directional coupling here. The end of that blade is moving up and down in response to the aerodynamic forces exerted on it by the air going past it. So, yeah, it's working. We've got it to work. And this is a cross-section demonstrating exactly the same thing. Obviously, it is settling down to a steady-state position. So it started off in the middle of the domain, rapidly moves off, and then sort of settles around in what I would guess would be some kind of dynamic state there. Of course, in reality, this would be in a rotating frame of reference. And as I say, that's the next step there. And we're able to provide stress distributions in the blade at the 2 speeds, looking on both sides of the blade here, so top and bottom in each case, edgewise and flapwise direction, so quite a lot of information there coming out of the calculation. Deflections here, and this illustrates the comparison between the 3 meshes. And as I say, we're not quite at the level of mesh independence, but there's some degree of correlation here. We're getting towards a reasonable prediction for the displacement in the Y direction in both cases, and actually in the X direction in both cases. But I didn't manage to extract those diagrams from Rachel's thesis. They didn't come out for some reason. So I should have gone back to and got them back, because they illustrate the full calculation here. Okay, so that's demonstrated we can do the calculation, but are we getting any kind of the right answer? At the moment, we do not have any experimental data to compare with. We're actually working with a group in Turkey, and the abstract for this presentation contains a number of other names of collaborators there, and the original hope was that they have a wind tunnel, and we were hoping to get some experimental measurements done by now for further comparison, but as is the way of things, we haven't quite got there yet. So future work is to do some measurements to do the comparison, but at the moment what we have is comparison with FAST, or possibly OpenFAST. This is a tool developed by NREL in America. And it's a lower fidelity wind turbine design code developed using technologies such as actuator line modeling and beam deflection. It's extensively used in wind turbine calculations, but it's a lower fidelity model. So we have done some comparisons here between our calculations and these in the lower fidelity model. I'm emphasizing this is a lower fidelity, both in the aerodynamic terms and also the structural model here. We're not expecting perfect agreement. We're expecting to show we're in the same ballpark. And that's exactly what we've got here. Different meshes here compared to FAST at the top there. We are getting the same sort of size deflections at the two speeds, but we are not getting exact prediction here, but then we don't know whether or not FAST is giving the right answer for this case either. So ultimately, without the experimental data, all we can say is we're getting similar answers here. So that's the end of my presentation. I hope you've enjoyed it. Our conclusions, we've built an FSI model here for an important technology here, wind turbine blades. It couples OpenFOAM and Calculix using the precise coupling library. We've validated that against a standard benchmark study for a cantilever plate, and we've applied it to investigate the deflections for a parked wind turbine blade and demonstrated some interesting results from it. There are discrepancies in detail, particularly compared with the low fidelity model, but in general, it works. Where are we going with this? Well, as I say, we want to validate against experimental work for the blade case. We want to take the mesh refinement and mesh convergence further to get a mesh which works for the Spalatal mass model in more detail. We'd like to include blade rotation, so we'll be able to look at structural behavior in power production, and also we should be fairly straightforward. We should be able to include a more realistic blade structure, and that will feed into these other aspects. So that's my presentation. Thank you very much for listening, and I'll take any questions.
Thank you very much. Are there questions from the audience?
Yeah, thank you for a very nice presentation. I was just thinking about including blade rotation. Is this something that is available in this Calculix, or is this something you need to develop on your own?
I hadn't thought of it from the Calculix side. I mean, from the OpenFOAM side, I'm regarding it as a fairly straightforward alteration. Use SRF foam, basically, in a cylindrical domain. I've got to think about the physics here, but I would presume we could include any necessary Coriolis terms and centrifugal terms into Calculix as explicit forces if necessary. But yeah, that's a good point. I hadn't thought about that.
Yeah, I just assumed that it was the Calculix that was the problem and not OpenFOAM when it comes to the rotation. But
yes, yeah.
Thank you for your
You may have been aware of course, I know very little about Calculix or stress calculation, so I've kind of been brushing over a couple of the lines in my presentation there.
Are there more questions?
Thank you. Really interesting talk. Building on that, would you say that it might be easier to then use solids for foam or a monolithic approach if you were moving to that rotation where it might be a bit more integrated, or do you think the coupling approach would still be the best way?
I don't know. I'm on the fence on this one. I don't have any great dog in the fight here. I can see benefits to a closely coupled approach, such as solids to foam, where you're able to solve everything in the one package, and that, for example, gives you ultimately the possibility of doing things like block solver and really coupled solution. But equally, I can see practical benefits to code coupling. So this works, basically. I'm quite pragmatic sometimes. I'll take a working solution. And it's a solution which leverages a lot of experience with FEA for stress analysis in the wind turbine industry. So it may well be practically a good way to go from that point of view.
Thank you very much. My second question was, have you thought of any optimization routines in terms of blade geometry optimization to integrate with this as well? Because that's one thing I struggled with in my undergraduate.
Yes, yeah. You may be aware that I'm quite interested in this Bayesian optimization tool. So once we get to the stage of being able to run these calculations, they're expensive to do, but the advantage of Bayesian optimization is you can squeeze the maximum amount of information out of a very small number of actually evaluations. So again, once we've got this working, we can throw it through something like that and optimize the blade. Yes, that would be great. And it would be an interesting thing because you've got a number of different possible optimizations, torque, power, but also maximum stress and construction costs.
Excellent, thank you very much.
No problem.
So are there more questions from the audience?
Okay.
Okay, from my side, can you give a statement on the computational costs, like what you invest if you compare to just fluid, just a CFD simulation and then the FSI overhead?
I don't have the numbers to hand. There are obviously CFD and full FSI has been significantly more expensive. Rachel's work started off with these low fidelity simple models which are commonly used, and she's looked at successively more sophisticated and detailed modelling processes, but it has shown the degree of cost involved here. And for a lot of current modelling, probably the costs are too far for what we need. But we're looking ahead, a couple of years' time, 5 years' time, then this sort of thing will be very accessible and quite likely just what we need for optimization.
Okay.
So I'm sorry, I don't have the numbers.
Yeah, okay. Thank you very much. So, maybe are there questions from the chat? So there's one question, which is, sorry.
No problem, no problem.
Did the fast model results vary much with the number of elements chosen for the actuator model?
I think that the fast model is the optimal calculation within fast. Rachel did a lot of work understanding how to use fast, so she has designed that bit to work as well as she possibly could.
Okay, if there are no more questions, thank you very much. No.
Thank you.
Okay, so our next speaker is Jonathan Fahlbeck from Chalmers University. And he's presenting on a low head contra-rotating pump turbine at unsteady conditions. Up to you.
Thank you very much. Yes, my name is Jonathan Fahlbeck, and I'm going to talk about the low head contra-rotating pump turbine. This work is made together with Professor Håkan Nilsson and Dr. Saeed Salehi and we're all from Chalmers University of Technology at the Department of Mechanics Maritime Sciences. So just some outline of today's presentation is that I will first go through pumped hydro storage, for those of you who don't know what it is, and then also show a future experimental test facility, so we will be able to validate the results sometime in the future at least. Then we'll go through developed pressure boundary condition, named head loss pressure, which you also can find in the OpenFOAM journal. And then just briefly show the numerical settings and then some results and conclusions. So moving on to pumped hydro storage. I'm apologizing for the online attendees, but I will show a laser pointer on the screen here, or on the whiteboard. So pumped hydro storage has been called a water battery, or can be thought of as a water battery. And this nice figure from the International Hydropower Association shows the sort of general layout of a pumped storage plant in cooperation with, for instance, solar power and wind power. And it's today the most economically viable solution to store energy on a large scale. And it helps providing grid stability and is thought to be a key component to have a fully renewable energy system without having coal and other sources for energy production. So typical layout is that we have a lower reservoir and a upper reservoir. The difference in height between these two reservoirs referred to as the head, or you can think of it as a pressure difference between them. And then these two reservoirs are connected via pipelines, and then there is a powerhouse where we have a pump turbine unit. In this research is carried out within the Horizon 2020 EU project named Alpheus, where we investigate low head pumped hydro storage, and one of the technologies that we investigate is this contra-rotating pump turbine unit. The basic principle of it is that the upstream runner, if we think that the flow is from in this direction, from left to right, then the upstream runner will swirl the flow, creating it or inducing a tangential component to the flow, and then the downstream runner will make use of this swirl velocity and then deswirl the flow. So moving on to the future experimental test facility. We can see here that the test facility, which will not be carried out by myself, it will be carried out as part of the European research project. But the test facility will consist of an elevated tank and a lower tank. So we will have open water surfaces in the experiments, and in the simulation we want to mimic this entire test facility, but without including the entire test facility. So you can see down here that this is the size of the numerical domain. If we compare to the full experimental system, we see that we will have a number of different components that we do not consider in the simulation itself. For instance, we'll have valves, bends, entrance and exit effects. All this will affect the overall system balance between pressure and flow rate. So in order to account for this, we need to include all these. Sorry, now I pressed the black button. Is it possible to get the presentation back? I'm asking the control room. Like that. Yes, in order to include all these different system components, we have developed a new pressure boundary condition, and it's named pressure or head loss pressure. And in principle, we apply the classical Bernoulli's equation, which I guess you all remember from basic course in fluid mechanics, at the computational boundary. So if we consider this very small hydraulic system, we apply this Bernoulli equation at the boundary of the computational domain. So the pressure at the inflow patch here would be equal to the static pressure at the reservoir minus the dynamic pressure minus the dynamic pressure difference at the patch and the reservoir. But since the reservoir is regarded as quite large, we can assume that the velocity at the reservoir is 0. Then we also need to add the hydrostatic pressure, and then we subtract the various losses. So we have minor losses from bends, instruments, and so on, and then we also have friction from the pipe. So with this new boundary condition, we can include all of this. So we can have specify any number of minor and friction loss factors, and we have also included some time varying possibilities. So for instance, we can vary the head or vary one minor loss coefficient, for instance, modeling a valve closing sequence. I showed the simulations of that in the last OpenFOAM conference or workshop. And one important thing is that for inflow cases, the losses are subtracted since the losses are they are upstream, while for an outflow case, the losses needs to be added to the patch since they are downstream. And this is developed in an incompressible formulation. So if you think this is interesting, you can check out the OpenFOAM journal and download both the source code and the paper. And just to do some advertisement, apparently it is the most read paper so far in the OpenFOAM journal. So continuing with some solver settings. So Unsteady simulations in OpenFOAM 2012. So we apply this head loss pressure boundary condition. We set the gross head to 6.45 millimeter or 6.5 meters, which is according to the test facility. And then we also include different parts from the test facility, from some bends and so on. And for velocity, we use the pressure inlet outlet velocity. Turbulence is modeled with the Q-Omega SST SAS, so we model parts of the turbulence spectrum. And we use a mesh size of 12 million cells. And here's just a table with some various solver settings. So for instance, we're using the backward scheme for temporal discretization and the last scheme for divergence of velocity. We use the smooth solver together with Gauss-Seidel for velocity K and omega, whereas we use the GMG solver for pressure. We use the Pimple algorithm, which is in this work configured to have a maximum of 10 outer corrector loops and 2 inner corrector steps, plus 1 non-orthogonal corrector. But we have some constraints, or some convergence constraints. Usually we attain a converged solution within 3 to 4 outer corrector steps. So having a closer look at the numerical domain, we have divided the domain into 4 different cell zones or mesh regions. So 1 low pressure zone and 1 high pressure zone. And then of course we have the 2 runners. I will refer to as runner 1 as this red thing, and the runner 2 is the blue part. And these 2 runners rotate individually in the numerical domain. And we use the IMA interface to transfer fluxes between the different mesh regions. So just looking at some results here in turbine mode first. So one of the things that we want to see is roughly what flow rate we can compute with this pressure boundary condition. And we achieve 285 liters per second, and the hydraulic efficiency of the turbine is at roughly 90% here. This 285 liters per second is roughly what the guys at the labs say that, okay, this is a sort of a good operating point if we can manage this. So I hope that this is the type of flow rate we can achieve in the reality as well. And here's just a snapshot of velocity magnitude. And we can see that there is a quite large variation after the machine, so there is a lot of things happening in the flow. I can also mention, I think I've got it, that in turbine mode the flow is from in this direction, so from right to left, or according to the arrows. And if you look at the flow structures with the lambda 2 criterion, you can see that we have some typical characteristics within the flow field. So we have these nice horseshoe eddies close to the larger support struts, but then we also have a quite large vortex shedding from both the large support strut, but also from the smaller support struts. And then we are also capturing this blade vortex shedding. You can see there is quite large interaction between the structures moving from the upstream to the downstream runner. Continuing to the pump mode results, to start with, the flow is now in the opposite direction, so going from left to right. We can see that here we have a computed flow rate of 267 liters per second, However, we're at a slightly lower efficiency at 87%. In turbine mode, we reach 90% hydraulic efficiency. The general things to state here, if you look at this cut plane of velocity magnitude, is that you seem to have quite large variation of the flow field after the two runners, so it is quite disturbed. So looking at the flow structures here as well, I will just go through this quite fast because it is similar as we saw before, that we have these horseshoe eddies and then also vortex shedding from both support structures and also these blade tip vortices. Worth to notice that it's quite much longer structures, or the blade vortices are longer in pump mode than in turbine mode. Now, anyone who works with the pumps, they know that it's usually is a problem with cavitation. So we have tried to, or we have just started to analyze this. I must stress that this is very preliminary studies that I'm showing right now. I actually put these two last slides together yesterday. But if we look at the design point, I should just state that this is not the point that we looked at in previous slide. In previous slide, we looked at this operating point that I just said. But at the design point, this is this column here, the left column, and the operating point that we sort of now regard as the more suitable operating point is the middle operating point. And the main difference, or the only difference, is that we vary the rotational speed. So for the operating point that we think is slightly better, is we have a quite lower rotational speed. So why do I say that it is better? If we look at, this is just the isosurface of the vapor pressure. So these simulations do not include cavitation per se, but this is a measure of the sort of likeliness of cavitation. So we see that for the design point, we have quite large regions by the runner blades, but also already at the support structures, we have a risk of cavitation, whereas in this alternate operating point, there is just a small amount of risk of cavitation by the leading edge of the upstream runner. And this is sort of what is new. The other things I could collect anytime, but we have started to run cavitation simulations, and this is only done for this alternative operating points as we see in the middle. And for this cavitation model, we use the interface change dynamic MyFoam solver. We have a two-phase mixture with a Scher-Sauer mixture model, and really stressing preliminary. But we also apply this head loss pressure boundary condition here. And the isosurface right now, the blue one, is showing a volume fraction of 0.5, so roughly regions where we supposed to have, or where we can expect to have cavitation. So we see that there is some risk at the leading edges here as well, but also at the leading edge of the downstream runner, as it seems. So perhaps we need to decrease the rotational speed even further, and this is sort of the present studies that I'm doing now. So here, just to show a small animation of the isosurface of where we have a volume fraction of 0.5, so just play this. So you can see that the front, or the cavitation front, it moves quite a lot on the blade surface. So I would say that even this operating point, we probably have quite large risk of cavitation zones on the blades, which may be damaging. And I know that the guys in the lab, they ask me, please run simulations or come up with operation points so we can avoid cavitation. So, and just to show similarly in turbine mode, this is just the isosurface of the vapor pressure here in turbine mode, but there is a small region of risk of cavitation at the trailing edge of the upstream runner. Flow is from right to left now. And our preliminary simulations suggest that we don't actually have a volume fraction that is below 0.5 in this turbine mode simulation, so perhaps the risk of cavitation is quite low or insignificant in this mode, hopefully. So just to conclude this work, we have looked at a low-head counter-rotating pump turbine. We saw that it is a quite complex flow field predicted by the unsteady fluid simulations. There is a clear rotor-rotor interaction between the two runners, and we have some quite large vortex shedding from the various support structures, both the low and both the large and the small ones. And with this head loss pressure boundary condition, we could estimate the reasonable flow rate, or I should say we hope that we can do this. And it provides a quite simple method to model larger systems, and we can include system changes with function one statements. And as I just demonstrated right now, it's possible to use with cavitation simulations, which I thought was nice. And the next step is to sort of finalize this cavitational analysis and see what comes out of it, and perhaps find some more suitable operating points in pump mode at least. And then once the experimental things actually take place, we will of course validate the numerical framework. So right now my simulations are perfect, but in half a year or so, perhaps they will be crappy. We'll see. So thank you very much for your attention, and of course I'd like to acknowledge the LFE's Horizon 2020 project, SNCC for providing computational support, and OpenFOAM developers and community. So thank you very much.
Yes, thank you very much for your talk. Are there questions from the audience?
Thank you. I wanted to ask you about the type of machine that you choose for this reversible work, because this is an axial pump turbine.
Yes.
And I think you said only 6.5 meter head, and the amount of water sounds like it's the real thing. Is 6.5 meter head enough for you to achieve what you want, or do you need a centrifugal machine further down the line?
Yeah, I think I was a bit vague about this. The 6.5 meter head, it is for the experimental test facility, but the sort of prototype scale or the full type scales that the research project actually evaluate is heads between 2 to 20 meters, so it is actually within that range. But then, of course, the machine will be much larger. Here, the diameter size is, I think, 0.3 meters, but the full-scale machine would be a 6-meter diameter machine, so it is quite large machinery we're talking about here.
Thank you.
Okay, more questions?
Hi. I just want to ask, in your boundary condition, because there was one additional term which is delta P friction, I mean, how will you estimate this? Like, if let's say you were to combine this boundary condition with this actual rotating rotor, how are you going to estimate those quantities?
Yes, within the boundary condition, I include, here we have the general equation. So the question is basically how I calculate this term, right? So I use the, what's it called now, the Colebrook equation, and solve the friction factor iteratively with this boundary condition. So it will be a function of the flow rate, diameter, and surface roughness in the parts that are not included in the numerical domain. So in this boundary condition, you need to specify the length of the pipes, but also the surface roughness. But then the flow rate, it will come as a result of the balance between pressure in the system. So it's solved, the friction factor is solved iteratively in the boundary condition.
Okay, are there more questions? So one question from my side, how long does it take to change from pump into turbine mode? Did you evaluate that?
I have run some preliminary simulations of this, but it's not, to this date, it's not decided exactly how such operations should be made. My current studies also concerns startup and shutdown sequences, and for this model scale, at least, we are thinking about times of 3 seconds roughly, but then it's just shutdown, but then of course you need to start up the machine, so say perhaps 10 seconds for this model scale if we can control everything nicely. For the prototype scale, this is supposed to happen later in the research project, so we have not started evaluating a reasonable time scale, but hopefully we can sort of use this. There are a number of scaling laws within hydropower that we can use as a sort of rule of thumb to get the first estimate of roughly how long the shifting times will be.
Okay, thank you very much. I don't see questions here from chat. If there are no more questions from the audience, thank you very much again for your talk. So, yes, we have one online speaker now. Hello.
Hello.
So can you share your slides with us?
Okay. Hello again. My name is Saeed. I am a postdoc at Chalmers Division of Fluid Dynamics. And today we'll be talking about transient operation of Kaplan turbines, both from physics and also from the challenges in numerical challenges in OpenFOAM. So basically, the transient operation of hydraulic turbines refer to varying operating conditions. So nowadays, because of the growth of intermittent renewable energy resources such as solar and wind, which are intermittent, we need some tool to regularize the grid. So nowadays, this is the job mostly for the hydraulic turbines, and the problem is that during varying conditions, very hazardous and harmful fluctuations and instabilities occur that needs to be studied. So many things change during such kind of conditions, like turbine load, flow rate, or even the geometry of the turbine, like the guiding angles, the runner blade angles, or even the rotational speed of the runner. So let's quickly have a look at the OpenFOAM, how OpenFOAM handles the dynamic mesh. So basically, one of the most widely used approaches is the Laplacian smoothing algorithm, in which that we solve the Laplacian equation on a deforming mesh. So this gamma here is the mesh motion diffusivity, which is usually distance-based, and the V is an arbitrary field. It could be displacement field or the velocity field. That we will talk about it soon. But the thing is that in order to deform a mesh, we need to find the displacement of each point in the mesh. But OpenFOAM is a cell-centered finite volume mesh, so conveniently we solve the displacement of cell centers and not the points. And afterwards we interpolate that onto the points. So I am aware that in the early versions of OpenFOAM we actually had some solver to solve specifically the displacement of the points. And if I'm not much mistaken, it is still available in foam extent, but for some reason which I don't know, maybe somebody could comment on that later. For some reason that is now removed from OpenFOAM, and we just solve for the cell centers and then interpolate it onto the points. So there are mainly two approaches here. Basically, you can solve these Laplacian equations either for the displacement of the points or velocity of the points. And in each case, the new mesh will be found kind of differently. So in case of this displacement Laplacian, we find the total displacement of each point, and we add it to the sort of initial mesh, the mesh which is inside the constant folder. But in terms of the velocity of the points, we add this current displacement in each time step to the previous mesh, to the mesh that belongs to the previous time step, not the initial mesh. So this is a simple example of a deforming mesh for displacement Laplacian and for the velocity Laplacian. you can see that naturally, whenever the displacement is larger, the velocity is minimum, and when the velocity is maximum, the displacement is minimum. But what are the advantage and the disadvantage of each scheme? So basically, one could say that displacement solvers, because they solve for the total displacement with respect to initial mesh, are not well suited for the large deformation. So I have a very simple example of a large deformation here. You can see if you apply the displacement solver, the solver becomes unstable quite soon, and the mesh is destroyed. You have a lot of negative volumes. But the velocity Laplacian can continue for a much larger deformation. So for large deformation, the velocity Laplacian solver is much more preferable. But what about the displacement solver? So when we have an oscillatory movement or motion in which that an object moves and then goes back to its original position. In this case, as you can see here, well, we solved this oscillation with both displacement and velocity. There is not much difference that we can see here. But if we look at the mesh, at the original position, when this oscillating item in the center goes or reaches its original position, and if we continue the oscillation for a long time, you can see that the velocity Laplacian, there is like a residual deformation which grows in time in the velocity Laplacian, but not in the displacement Laplacian. So in case of oscillations, the displacement Laplacian works much more efficiently, because when we go back to the original position, we are actually solving for a zero field, and we definitely will get our original mesh, but not in the case of velocity Laplacian. So back to the Kaplan turbines. In case of transient operation in Kaplan turbines, we have as you can see in these two movies, we have both rotation of runner blades and guide vanes. So, and at the same time, that runner is rotating with full speed around around the turbine axis. So previously, we have developed a framework for this, and we actually presented it in the previous workshop. But the previous framework that we developed was based on the displacement solver, and we had a lot of problems with the stability of the dynamic mesh. So because in Kaplan turbines we have large deformations, but we don't have real oscillations. Naturally, it is expected that a velocity-based solver should perform better or more robust. So what we did is that we further developed this library, and now we actually developed a new library which is based on the velocity Laplacian solvers. So as we expected, the new library that we recently developed is much more robust than the previous displacement-based solver. And by robust, I mean that we could refine the mesh much further. So we could use a much finer mesh, which is very much preferable for us, because this is a very complex flow, very high Reynolds, and in order to simulate it in much more details, we need a much finer mesh, but we couldn't get it with the previous framework. But with the new framework, which is based on the velocity Laplacian solver, we can do it. We can actually have like around 20 cells in the clearance. But before, with the displacements Laplacian solver, we couldn't go much more, 5 cells in the tip clearance. We tested this new framework that we developed, and we actually compared it with two well-known commercial softwares, namely Fluent and CFX, and we showed that this frameworks actually outperformed these two solvers significantly. So in this case, this is a simple case. This is just one single guide vane of a Kaplan turbine, but the surfaces are highly curved. So upper and lower surface are highly curved, and we have a hub clearance here that you can see also a clearance between the lower surface and the blade. So these curvature and also the clearance makes this is a very tricky problem. So as you can see, this is the number of non-orthogonal cells, and by non-orthogonal cells I mean the cells with non-orthogonality more than 70 degrees. And for Fluent and CFX, they grows very rapidly, and also Fluent produced the first negative volume after 6 degrees of rotation, and CFX produced the first negative volume after 7.5 degrees. But our frameworks can rotate this guide vane up to nearly 14 degrees. Here again, you can see the deformation of the mesh near the clearance, and the mesh with the standard OpenFOAM with ANSYS Fluent and ANSYS CFX is destroyed after some rotation, but with the developed method, it can further deform the mesh. So we tested this on a full Kaplan turbine. But full, I mean the full geometry, but this is a still a model turbine. It's not a full scale. So it's a model turbine and with 6 runner blades and 20 guide vanes, and the experimental data are available only during steady operation, but we are looking at the transient operation. So the full model contains 15 million cells here. We are using SAS. The framework is developed in OpenFOAM 2112, backward and loss-for discretization. The inlet we are using a fixed total pressure, so the flow rate is actually being adjusted like automatically according to the geometry. So when the guide vanes are closing down, the flow rate is automatically reduced through this boundary condition. So here you can see the guide vane angle and runner blade angle, which are decreasing. So the guide vane is closing down for 6 degrees, and runner blades is closing down for 5 degrees, and the whole transient procedure is happening during 4 seconds. But the total simulation time, including the stationary best efficiency point and part load, is taking in 9 seconds. So it's a very heavy simulation, not just because of the mesh. It's not too crazy. It's just 15 million cells, but because of the total simulation time, which is if you also account the first 6 seconds that we solved to reach stationary condition, it's 15 seconds of flow time, physical time, which is a lot. So validation, we have validated with the experimental data at the stationary condition. So you're now seeing the profile on this red line here. This is the axial velocity, this is the tangential velocity. Of course, there are some disagreements, especially around the center of the draft tube, but this is very common, and almost all of the numerical studies in the literature that assessed this specific test case reported such differences. So it is possible that the experimental data has also some errors. Moving on, you can see the deformation of the mesh during this best efficiency point, which is the left column, and the part load, which is the right column. So this is the guide vanes of the turbine, and Similarly for the runner blades, as you can see, the clearance of the runner is closing down when we go from the best efficiency point to part load, which makes this procedure much more challenging. The clearance at its minimum is like 0.5 millimeter, and we are deforming the mesh in that clearance. So the quality of the mesh during this procedure, of course, changes, but it is the non-orthogonal angle or the average non-orthogonality of the cells is increasing just a little bit. So it's one could say that the quality of the mesh is still quite good after the mesh deformation. So the average non-orthogonality is increasing just like one degrees for both runner and guide regions. When we look at the flow field, well, many things are happening. We have now two probes here, probe 1 and probe 2, and we are now looking at the results of probe 1, which is right before the runner, upstream of the runner. As you can see, when we close down the guide vanes and the flow rate decreases, the pressure at these 2 points increases. And as you can see, we have like a band of variation, which is basically the rotor-stator interaction. So when we look at the spectrogram of this pressure fluctuation, so if we subtract the instantaneous pressure from the instantaneous mean, we'll get a fluctuation, and then if we get the FFT through time of that signal, this is the result that we get, which is called the spectrogram. And a spectrogram of this specific pressure shows a very significant excitation of the runner blade passing frequency, which is shown here. And we don't see really a lot of effects of low frequency excitation as we expect in the part load. So we can see some effects of low frequency here, but it's not very significant. But when we go to the probe number 2, which is inside the draft tube, you will see that we have a lot of low frequency excitation. So mostly because of the vortex stroke, the rotation, and the breakdown of the vortex. Both vortex created due to the load rejection condition, and also the vortex shedding behind this blunt runner cone. So so a lot are happening inside the draft tube, which results in the very large band of low frequency excitation in the spectrogram. So if we look at the lambda 2 criterion from best efficiency point to part load, you can see when at the part load we have a very slender vortex stroke, but when we go further down, when the load reduces, this central vortex becomes stronger, and the oscillations becomes much more significant. As you can see here, now it's much more significant and stronger. But one thing that is that was kind of strange or interesting for us, we don't see a clear evidence of a precessing vortex stroke. So there is no like a vortex stroke that is rotating around its center. That there might be a few reasons for this. One is that we have double regulations in the Kaplan turbine. So it is possible that because of the regulating the runner blade, that the rotating vortex stroke is avoided here. So if we compare the best efficiency point and the part load of this particular Kaplan turbine, you will see that the vortex stroke is swelling and it's getting stronger with load rejection. So we further developed our previous framework, and now the framework has both options, so displacement Laplacian or velocity Laplacian, which based on the description and also the experience that we have, the velocity Laplacian is more preferable for Kaplan turbine. We showed that the framework outperforms two investigated commercial safety software. We also tested and verified this framework on a Kaplan turbine, and we successfully simulated the flow field. So all the codes and test cases are also available on my GitHub. I should just mention that unfortunately this Kaplan turbine is a commercially is owned by a company, so we cannot present this specific test case, but there are some simple Kaplan turbines and like tutorial test cases inside this framework that we call it Kaplan-FOAM. So thanks to the SVC for providing the funding for this research and for the SNCC for all the computational resources that we have access to. And thank you to you all for listening.
Yeah, thank you very much for the talk. Are there questions from the audience? Okay, so there's one question in the chat. So
Yes,
just
please.
asking if you considered radial basis function for the mesh deformation.
Yeah, I assume that's for the mesh deformation. I actually have looked into that, but no, I haven't applied it on this specific test case. I know that it is available in Form Extend, and I have some experience working with that, but no, not yet. I have not used it for the Kaplan turbine.
I had also very nice experience with radial basis functions, so I think it's quite good. It gives you, for large deformations, it's a good approach. Are there more questions? Are there questions here from the audience? So then I would ask, when you talk about partial load, what are we talking about? How much percent of best point?
Well, there is no like a global definition for part load or partial load. Usually when we go lower than best efficiency point, we call it part load. And when we go very low, some people call it deep part load. But here specifically in this test case, it's 75% of load. So the flow rate is 75% of the best efficiency point flow rate.
Okay. And did you also consider to change the rotational speed of the turbine itself as a third like parameter that you can tweak on in partial load? Is that a topic for you, or?
Yeah, that is actually on our to-do list. But the thing is that we are working with the experimental facility that are working on the experimental case, on this specific test case, on the experimental measurement. But in the transient operation in this turbine, the turbine is always connected to a generator, so that the rotational speed is always constant, even we go into the deep part load. So that's not something that we want to do specifically for this procedure, but yeah, still it's on our to-do list to add to our framework.
Yeah. So I think if it's like smaller Kaplan turbines, so it depends a bit on the class you're talking about, but it seems to be coming up that you run like inverters, so you can easily change the rotating speed as you want. So you're quite unlimited in that. But okay.
I thought you mean flow-driven rotation, but yeah, changing rotational speed in time, yeah, that is already possible with this framework. But I thought you mean like 1 degree of freedom flow-driven rotation.
No, okay. Are there more questions? So, okay, so thank you very much again for your talk. And then I would close the session for today. Thank you for attending.